So, welcome back everyone. In this lecture, we will continue the definition of nilpotent Lie algebras and then see some of its basic properties. Okay. So, let us first recall how we define this nilpotent Lie algebras. So, first we define what is called this lower central series. So, you start with a Lie algebra. Over C. So, then we have this following sequence of ideals inside C called lower central series. So, this is defined inductively. So, first you take G naught to be G and then G 1 to be the bracket G G, the derived algebra, and then G 2 to be the bracket of G with G 1. Okay. So, this is very different from the derived series. So, and so on. Suppose let us say we have defined G power n and then G power n plus 1 is defined to be the bracket G with G power n. So, then the sequence, so this G I where I greater than or equal to 0, this is called lower central series. Okay. So, because if you think about it, if you take G n and then go modulo that G n. So, if you take G and then go modulo G n, then what is the definition of G n plus 1? So, G n plus 1 is actually equal to G G n. Okay. So, in particularly if we look at so this G n plus 1. So, the G n plus 1 will be actually contained in G n. Okay. So, I guess we should go modulo G n plus 1. So, then it is clear that if we take this G n modulo this G n plus 1. So, this actually lies inside the center of G modulo G n plus 1. So, just from the definition. Okay. So, because this G, so if we take any element from this left hand side G n modulo G n plus 1, then it is easy to see if you compute x with any y plus G n. Okay. So, then what we get, this is x y plus G n plus 1. Okay. So, we are computing this x plus G n plus 1, y plus G n plus that commutator. So, that will be bracket x y plus G n plus 1. Then you can see that since this bracket x y is an element of G n plus 1. So, since x y is in G n plus 1. So, this implies the bracket x plus G n plus 1, y plus G n plus 1. So, that is 0 inside G modulo G n plus 1. Okay. And this is true for any y in G. So, that means this G, if you take this center of G modulo G n plus 1, that should contain this G n modulo G n plus 1. Okay. So, because of this we call this as a central series. Okay. Every time when you go modulo the previous thing, so that the new thing will be actually like G n modulo G n plus 1 will be contained in the Z modulo G n plus 1. So, using this also one can actually give a characterization for nilpotent Lie algebras. Maybe I will state that in the problem sheet. Okay. Let us move on. So, here is yeah, very here is an important example. Okay. So, if we take the strictly upper triangular matrices, so that must be nilpotent. Okay. This is a very important example. You start with what is called this strictly upper triangular matrices, the set of all n by n strictly upper triangular matrices over C. So, we have seen that this is a subalgebra of set of all n by n matrices, okay, or the general linear algebra. So, we claim that this is indeed nilpotent. Let us consider this example, the set of all n by n strictly upper triangular matrices over C. This we saw that this is a subalgebra of GL and C, the general linear Lie algebra. So, if we compute the derived algebra of this, it is easy to see that it is actually spanned by all this Eij such that j minus I greater than or equal to 2. So, if we do more computation, I will leave it to you to check. So, this is something I will not verify, I will just leave it as exercise. So, if you compute G2, so this will be spanned by the vectors the elementary matrices Eij such that the level of that elementary matrix is at least 3. Okay. So, now you can see the pattern. So, and so on. So, if you take any g power r, so that will be spanned by the elementary matrices Eij such that j minus I is greater than or equal to r plus 1. So, that implies, so when r is at least n plus 1, so then it is clear that this g power r will be 0. So, that implies, so this Lie algebra is actually nilpotent, Lie algebra. So, this is a very important, this is a very important Lie algebra. So, we will see later that any subalgebra of nilpotent Lie algebra must be nilpotent. So, that is some easy fact. So, indeed we will prove the Engel's theorem as one of the application of Engel's theorem. We will get any nilpotent Lie algebra can be realized as subalgebra of this strictly upper triangular matrices. Okay. So, that is the very important structure theorem about nilpotent Lie algebra. So, that is our aim today. So, let us actually move on. So, if we take this triangular matrices, so which we actually denoted by T and C. So, this is set of all upper triangular matrices. Okay. This is actually not nilpotent. So, this is solvable, but not nilpotent. So, it is not hard to see if you compute the derived algebra of this T and C. So, that will be strictly upper triangular matrices. But if you go to the lower central series and then compute G2 for example, so that will be T and C comma N and C. So, that will be again N and C. So, you will not go down. So, this actually kind of tells you that. So, this is something I will leave it to you to check. So, this immediately implies if you compute any g k, so that has to be this the derived algebra of G, which is N C. So, that implies this T and C will never be nilpotent. Okay. So, here is another simple example that we have already seen. So, which is again solvable, but not nilpotent. Okay. So, if you take for example, this G2 non-abelian, so which is spanned by two elements x and y, such that x y being equal to x. So, if we compute the derived algebra of this, so this will be one dimensional, but if you compute G2, it is not hard to see, this is again one dimensional Cx. So, this implies actually Gk is again one dimensional. So, in particularly lower central series will never go down very strictly. So, that means G is not nilpotent, but we have already verified G is actually solvable. Okay. So, G is solvable, but not nilpotent. So, that means the class of solvable Lie algebras is strictly very big class, okay, then class of nilpotent Lie algebras. And we will see later that there is a very close relationship between the class of solvable Lie algebras and the class of nilpotent Lie algebras. Okay. So, that is something we will actually prove. So, here is some important properties of this nilpotent Lie algebras. So, you start with the Lie algebra. Okay. So, here is the proportion. The first statement, if G is nilpotent, so then its subalgebras and homomorphic images, all of them are nilpotent. All subalgebras and homomorphic images. Okay, this is again easy to prove. So, what is the proof? So, just look at K, which is a subalgebra of G. So, then it is not that difficult to prove if you compute K power I, which will be subset of G power I. So, that means whenever G power I is 0, that will imply K power I 0. So, that proves any subalgebra of a nilpotent Lie algebra is nilpotent. So, for the quotient, if you call pi is a quotient map from G to G dash, which is a surjective map, let us say Lie homomorphism, then one can easily check if you compute pi of G I. So, that will be equal to G dash of I. So, that will imply if G power I is 0, then pi of G I will be G dash power I, that will be 0. So, that again says the quotient is also, or the homomorphic image is also nilpotent. So, recall our example, this when we took this Lie algebra G2 non-abelian. So, when we computed this derived algebra, so that being one dimensional, so that is an abelian Lie algebra. So, all abelians are easy to see, they are all nilpotent Lie algebras. So, this is actually nilpotent. So, if you go modulo this G1, so then G modulo G1 again being one dimensional. So, this is just one dimensional. So, that will imply this is also nilpotent, or it is actually indeed abelian. So, this is in particularly nilpotent. But what happens, G we just saw that it is not nilpotent. So, even though there is an ideal which is the derived algebra, okay, that is being nilpotent, and when you go modulo that again we get nilpotent, the quotient is also nilpotent, does not imply that G nilpotent. Okay. So, this is actually nilpotent Lie algebras are somewhat restricted classes of Lie algebras. Okay. So, in this sense the solvable Lie algebras are much more important Lie algebras, because so they are actually satisfies this condition. Whenever you have ideal inside G, if I is solvable and G modulo I is solvable, so that would imply G is solvable. So, we will see later this property is actually somewhat very important property to check solvability, but this property is no longer true for nilpotent Lie algebras. Okay. So, that is actually kind of tells you that working with nilpotent Lie algebras will be harder than working with solvable Lie algebras. So, but is there any weaker version? Of course, there is a weaker version. What we can do? We can actually go modulo the center. So, center is always abelian. Okay. So, if you go modulo the center and then if you get nilpotent, so then we can assure that G is nilpotent. That is again not very hard to prove. Suppose G modulo center of G is nilpotent, then G modulo center of G some power k will be 0. So, that would imply that G power k will be subset of center of G. So, now if you compute G power k plus 1, which is the bracket G with G power k. So, that will be just a subset of the bracket G with center of G, but the bracket G with center of G is 0. So, that would imply that G power k plus 1 is 0. So, that means G is indeed nilpotent. Okay. So, this is actually one of the important checking. Okay. So, whenever you have this Lie algebra, if you want to check it is nilpotent, just go modulo the center and then see whether it is nilpotent. It's kind of reduces the dimension bit. So, now we can see that being nilpotent is actually somewhat very strong condition. Okay. So, what I mean by that? So, this lower central series that is actually converges to 0. Okay. So, that is what nilpotent means. So, in particularly, so if there is a k that is chosen minimally such a way that G power k is 0. So, then what will happen? So, choose k minimal such that G power k is 0. So, then it is immediate that G power k minus 1 will be non-zero. But what is the definition of G power k? So, G power k is nothing but the bracket G power k minus 1. So, that implies this G power k minus 1. So, this is inside the center of G. Okay. So, this implies G power k minus 1 is part of the center of G. Since G power k minus 1 is non-zero, so that means the center is being non-zero. Okay. So, if G is nilpotent, so then we proved that the center of G is non-zero. Okay. So, for some reason if you know that center is 0, then you can immediately conclude that G cannot be nilpotent. For example, semi-simple Lie algebras. So, we have seen that center is being 0. So, that means semi-simple Lie algebras will be never nilpotent unless they are 0. Okay. So, this actually kind of recalls some basic properties. So, here is some observation. So, we will actually unravel the definition of nilpotent and then see what it means in terms of this adjoint operators. Okay. So, let us say G is being nilpotent and then G power k plus 1 is 0. Okay. So, I can assume k is being greater than or equal to 0. Okay. You start with G being non-zero space. So, if G is 0, then there is nothing to actually worry about. So, then I can choose k such that G power k plus 1 is 0. Okay. So, now if you actually just write down the definition of this G power k plus 1, what is this? So, this is by definition bracket G with G power k. So, then if you unravel again, so this is just the bracket G with G and so on. So, you will be taking successive bracket up to some k number of 10 and then acting on G. So, this is k number of times, okay. And this is being 0, that tells you that if you take the successive brackets k number of times, okay, so then you will be getting 0. So, the leaves of this form, okay, coming from this space they are called right norm leaves. So, let us look at what we get indeed. So, if you just take this to be 0, this part to be 0. So, then this means, so for any x 1 etcetera x k in G and y in G, we get the bracket x 1, the bracket x 2 and so on, the bracket x k comma y is being 0. Okay. So, the leaves of this form are called right norm leaves. Okay. So, you can see that you can similarly define what is called left normed leaves. So, this is a very specific way of taking successive Lie products. Okay. So, in Lie algebra, because the Lie product being non-associative and non-commutative Lie algebra, Lie product. So, you have to be very careful in taking the products. So, the order in which you take the product matters. So, here we are talking about very particular order of taking the Lie product. Okay. This will be called right norm lever. So, if you write this in terms of this add x maps, then this is equivalent to add x 1 composition, add x 2 composition etcetera, add x k applied on y is 0. So, and this is true for all y. So, this says the map add x 1 composition etcetera composition add x k, this itself is 0, and this is true for all x i's. Okay. So, x 1 etcetera x k, for all x 1 etcetera x k it is true. So, in particularly if you take all the x i's to be equal, okay, suppose x 1 equal to x 2 equal to n etcetera x k, then we get add x power x k is being 0. Okay. So, that means what we have indeed proved, for any x in G, add x is nilpotent as an operator on G. Okay. So, that means all elements of G are add nilpotent. Okay. So, that is the conclusion. So, indeed we will prove later, so which is called Engel's theorem. Okay. So, this actually characterize the nilpotent Lie algebras. So, let me state the theorem. So, we will actually later prove it. So, this was proved by Wilhelm Engel. So, what it says, G is nilpotent. Of course, this is a finite dimensional space. Okay. If and only if all elements of G are odd nilpotent. So, that means add x is nilpotent for all x in G. So, this is actually one of the characteristics. So, even though this thing actually looks like add nilpotent being very weaker than this condition. Okay. So, this is easy to see. So, G is nilpotent if and only if you compose there exists k such that add x 1 composition etcetera add x k is 0 for all x 1 etcetera x k in G. So, that is just being definition. So, that is one of the characterization, but from this we are getting this weaker version add x being nilpotent. We are saying that if all elements are add nilpotent, so that would characterize the nilpotency of the Lie algebra. Okay. It is a very powerful statement. So, we indeed want to prove this. Okay. So, for that actually we would like to prepare ourselves a bit. Okay. So, here are some results that we have already seen. Okay. Let me just recall. So, suppose G is linear Lie subalgebra. So, let us say G is contained in GL of V, where V is 5 dimensional vector space. So, then we can talk about nilpotent elements inside G. Okay. If X is nilpotent, so then we proved that add X is also nilpotent. Okay. So, this is something we already proved. So, in a way, if you are interested in proving Engel's theorem, so you can see that Engel's theorem is actually equivalent to the following statement. Okay. So, let me call it E1. So, what is the statement? Suppose G is linear Lie subalgebra and all elements of G are nilpotent. So, then we say G is nilpotent Lie algebra. Okay. So, this is actually I would like to say E1 is equivalent to this theorem, Engel's theorem E2. Okay. For example, why E1 implies E2? Okay, let me call this E2 as okay, G is nilpotent. So, let me write only one way. So, let G be a Lie algebra. So, not necessarily linear Lie algebra, and all elements of G are add nilpotent. So, then we have G is nilpotent Lie algebra. Okay. So, why this is why E1 implies E2? E1 implies E2 because, so what we can do, so given G you always have this what is called this adjoint map. Okay. So, look at this add map from G to GL of G. So, then you know that add G will be isomorphic to G modulo the center G. Okay. So, now where is odd G? Add G is being subalgebra of GLG. You can see that the hypothesis actually says if all elements of G are add nilpotent, that means all elements of this add G they are nilpotent. Okay. So, that means using this E1 we can conclude that okay, using E1 we can conclude that add G is nilpotent. So, once we know that add G is nilpotent because it is isomorphic to G modulo center G. So, that implies G modulo center G is nilpotent. So, that means G is nilpotent from our earlier remark. Okay. So, this will imply G modulo center G is nilpotent. So, that would imply G is nilpotent. Okay. So, basically we proved that the statement E1 actually implies E2. So, now if you think about how E2 implies E1, okay, so what we can do, one can think G okay, as abstract Lie algebra. So, since all the elements of G are nilpotent, so then we using this remark we can see that all elements of G are ad nilpotent. Okay. So, then by E2 we get G is nilpotent Lie algebra. Okay. So, again this remark is used in order to prove E2 implies E1. So, E2 implies E1 can be proved using just this remark, let me call it 1. Okay. Using remark 1. So, you start with G such that all elements of G are nilpotent. Then using remark 1, all elements of G will be ad nilpotent. Okay. So, that would imply that G is nilpotent. So, actually I will stop here because we need some more preparatory work in order to prove Engel's theorem. So, that work I will do it in the next lecture. So, that important result will be called invariance lemma. So, that I will do it next time. Okay. I will stop here. Thank you.